All right, thank you all for coming out. I'm Scott. I work with SWIM. I'm one of the front-end engineers, but I tend to build a lot of non-front-end things because it's fun. Today, I'm going to talk about one of the applications I built out. That was one of our sample applications. Really quickly, I'll do an introduction of myself. I've been programming since elementary school. I started on a VIC-20 doing BASIC and moved up from there. Programming is kind of one of my passions. Like I said, professionally, my title is I'm a UI developer, but I do backends, middleware. Sometimes I do C++ for firmware. It's just kind of all over the place. But I mostly like doing UI because I like building things that people can interact with and look at and go, ooh, that's neat, and poke at it. And so that's fun. I've done both web and game development. I've worked on many variety of projects. I worked on the PlayStation Store for the PS3 long ago. I worked on the UI for the last SimCity game, which the UI was awesome, the server was not my fault. So I'm going to be talking about, essentially it's a hypothetical greenhouse. And we're using this to show essentially how we're grabbing data from sensors and streaming them to various devices in real time and using the sensor data to do various actions. The greenhouse itself, it's comprised of several devices. Actually, I'm just going to skip this. Each device essentially is a Raspberry Pi. It doesn't have to be a Pi on all of them, but they're all essentially a Raspberry Pi. All of them are running just a standard Debian, and then on that we run SWIM and we run Node. So there's three types of devices within our application. The main part is the plant monitor, and this little guy here, even though he doesn't have a plant, imagine a plant. This would be one of our plant monitors. And so the values that you're seeing here are real-time sensor values being read in from Arduino and crashing because I'm having a great day with hardware. So the real-time values get read into an Arduino here, and then in Node, I'm picking up those values and putting them into SWIM. And then from SWIM, they get propagated through a couple of different agents to enable, essentially we have alerts that can be triggered on a device and given to another device. And they communicate essentially the status of the greenhouse through various lanes within SWIM. And that's kind of what I'm going to go through here. So we have the plant monitor. We have an automated bot, which essentially is just another Pi that right now just has a sense hat on it. And so it's an 8x8 LED screen that we can show various animations and stuff. And so what that ends up doing is showing if there's an alert or something going on in the greenhouse, it'll show this red animation, and everything's good, it shows a blue animation. In a real greenhouse, that would actually do something useful, like turn on a light or water the plant or something interesting and useful. But since it's just a demo, it's more about just showing how we can communicate between the devices. And then lastly, we have the data aggregator. And that essentially sits at the top and listens to all the devices that are within its network and provides you an interface to see in real time what all the devices are doing at once. And then you can browse to the individual devices. Every single device has an associated web page with it. And so for like plant monitor, we have what's being shown there. That's just a web page being run in its native browser. And so it's just standard JavaScript. It does use the SWIM UI client to talk to the SWIM server to get that data. And so that's essentially how we build that UI. And we're also using our SWIM charts to visualize the data. And our SWIM charts actually make it really easy to basically link to a lane, get some values, and display the chart. And you don't have to worry about the intricacies of rendering the chart or anything like that. It's going to do it for you. And then we give you a lot of options to be able to skin it and make it look nice. So because every device has its own web page and is running SWIM and Node, when you start browsing the, unfortunately I can't browse too many here, But you can, let me see here. So if this was running as it should, you would see the bots listed here, and you could tap that bot and go to that page for that bot. But as you're browsing those pages, you're also physically browsing the devices, because every page is served from the device that it's representing, which is kind of an interesting way to do your hosting. There's not really a centralized host anymore. The host is every single device. Which works great if you're on like an internal network and everybody can talk to each other. It kind of falls apart when you have to go across networks. For example, I have, this is running on my desk at home, and it's attached to appliance, and it's doing all the sensor stuff. This can aggregate to an aggregator in EC2, but it doesn't have any visibility to anything that's, say this guy. It doesn't know about it because this guy is on its own little mini network. So your network topology kind of defines how these things can talk to each other and how you can access them. So yeah, really quickly going to try to go through kind of how each application or each part of the application works. The plant mon, as I said, you have Node, which is running Express for the website. We have SWIM, which is our data source, and then we have an Arduino, which is what's pulling out all that data off. You can see here, this is kind of the path of how things go. We pull sensor data from the Arduino into Node, into the Pi. That goes into Node and then into SWIM, and then this is essentially the page that you see there. The bot is very much the same. And let me back up one more thing I wanted to point out. Each of these have different types of sensors. And so for this guy, we have temperature, we have light, and we have the soil moisture level, which is kind of the really basic things you want to know about your plants. The bots have a bunch of sensors on them because of this sense hat thing. And so we are actually also pulling all of that sensor data into SWIM as well. And so we could act on that data. Say if like a bot fell off a table, we could probably pick that up and generate an alert for it. Again, we're basically pulling over serial into Node, sending it into SWIM, and then both of those can send down into the status page. And then the aggregators are fairly simple. They just sit on the network and wait for things to tell them that it's there. It doesn't know about anything until essentially a device comes online, starts getting sensor data, and reports that up to the aggregator. So it's a very bottom-up kind of approach. And it works fairly well because it makes it a very dynamic way of being able to aggregate a whole bunch of plants. You can bring in a new plant or take out a plant, and it doesn't really matter. It all really comes down to how they're configured. This is kind of the high-level overview of how the data flows. Again, all the plant sensor data, the bot sensor data, all that goes up to the aggregate. The aggregate can go up to a zone server, which would generally be off in the cloud somewhere. The zone server is really just another aggregate, but at a higher level. It's doing the exact same things, but it's just aggregating aggregators. And so there's a lot of configuration that goes on in the background because every, excuse me a second. So every device is running the exact same code base, and the configuration files that you give it define how it's going to act on that network. And so like this guy here, we have an address for its aggregate host, which is plantmon.swim.ai. That would be off in the cloud, basically running on the EC2 or Azure or wherever. The device name, Raspberry Ag3, we were going for simplicity in this implementation, and so part of how the device figures out what it's supposed to be doing is based on its name. And so it's going to do a substring to find ag, plant, or bot, and use that to basically decide how it needs to be acting. That also lets us have one device be all three. So if its name is Raspberry Ag Plant Bot, it's going to be all of those things. So it's a little bit of a hacky way to do it, and if I was to do it again, it would be just a straight up configuration value and not this weird like substring thing. But it did give us some interesting ways to be able to configure the devices. So this would be the configuration for the SWIM side of things. And so you see here we have the SWIM port. It could also talk over serially if it wanted to. Instead of having JavaScript do it, you could have Java do it. It's kind of whatever makes the most sense for the thing that you're doing. I like JavaScript, and so JavaScript is doing it. And then under Node, we have a whole bunch more configurations. So some of these are kind of repeats because Node and Java don't share the same configuration files because they process their configuration files differently. With Java, I can just give it this big JSON file and it's going to be like, oh, great, I know what to do with this. And it's very easy to use. So we define the bot name, how it needs to talk, what ports, and then these start defining the services that it uses. So if it's, this one I believe is an aggregator. Yeah, it's an aggregate. So sensehat is disabled, planned config is, should be disabled. And so by basically turning these on and off, you turn on and off the feature of that device. And so you could very easily change what the device is doing just by giving it a new config file and restarting the service. You don't have to change any code or anything like that. We also have a separate version of this that's all built into Docker files that we can use Azure IoT to publish to IoT devices. And in that case, some of these things actually end up as environmental variables inside of Azure. So there's various ways you can set these kind of config files. You don't have to do it this way. This is just what worked for me and for my app here. Cool. So now that I've kind of given you the rundown of like the high level of what the app does, I want to get into code and start talking about SWIM and lanes inside of SWIM. But first, we're going to talk about the plane. So the core of a SWIM app is generally you have a plane. I think you can have more than one plane, but I've never built an app with more than one plane. I just throw it all in my one. So within this plane, I'm defining my web agents. And each of these are going to be my web agents. These web agents are generated dynamically at the time that you call into it. And so, for example, sensor in this colon ID, that's going to be basically a variable. Any ID I put there, it's going to create a new web agent that is type sensor service with that ID. And I'll show you in a second what sensor does. And so that's kind of how all of these end up getting generated. Is they're not there until data starts using it, and then once data starts hitting it, all these web agents start getting created automatically for you. Which is really nice. You don't really have to worry about the setup and the teardown of the web agents. They're just there doing their job. So let's start with the sensor service. So there's a whole lot of lanes going on in here, and I'm going to ignore most of them and focus on kind of the important things. So in a sensor service, the most important thing that you need is the current sensor value. Otherwise, what's the point? And so, okay, sorry. So that's what this guy is doing. It's a simple value lane, and a value lane, basically, it's going to hold a value. It's not going to, it doesn't have history, it doesn't have any other things, it's a simple value. And so as sensor data is coming in, it's constantly updating this latest value. And when that happens, any client that's connected to this lane gets that update immediately. And so that's how we populate the UI is from Node, we shove in that sensor data here, it sends out an event to the UI that's listening for it that, hey, it's changed, here's the new value. And all of that happens fairly automatically just using the SWIM client. You'll see here we do some other stuff in here. Most of this is debug. This is important though. And you see it's within a conditional. So what's happening here is when the sensor first comes online, we need to start telling other things that it's there, there's a device, and it needs to be tracked. And so way down at the bottom here, here we go, send device to bot. So this method here is going to call a command lane on another web agent that is device. And it's going to say, I'm adding a sensor, and here's the ID. And so if we go to device, add sensor, this is that command line. So this is what's going to get called. What this is doing is creating what's called join lanes. Well, I'm sorry, it's setting up the join lanes. They are created, well, we'll just use this one as an example. This is a join lane. And what a join lane is going to do is essentially is going to go look at another lane, either within that same web agent or in another web agent, and get any of the updates that are coming in from that. And so what it's going to do first, in add sensor, we're going to create a downlink to that sensor that we just created and start listening for the latest. And so now, so now the device is able to listen to every single sensor that's registered on that device. So then the next thing that happens is we have to send it up to the aggregate, which is kind of the same thing. We do a command lane to the aggregate web agent. We're giving it a node, a key of the device name, and that will let the aggregate know that the device is online. And so, what's the method I'm looking for? Key property device name. Like I said, there's a whole lot of lanes going on in here, and I'm trying to simplify it because I think it's more important to talk about what the lanes are and how they do things. So yeah, here's another, when the aggregate comes online, it's going to call this, and that reports up to the zone server if it has a zone server configured. And so that is how it propagates up from the base, from a sensor, all the way up to the zone server. And as it's doing that, it's passing how to talk back to itself up to everything else. So that way, the zone server can go and talk back to the aggregate to get data. The aggregate can go and talk back to the devices to get sensor data. And you get that communication going both directions. So one other important lane that I kind of skipped over. So we have value lanes, we have command lanes, we have the join lanes, and then we have map lanes. And map lanes, in this, we're using for the long-term history of a sensor. So on this guy, stop it, there. This number up here is coming from a value lane. These graphs come from a map lane. And so what happens is every time we update the value lane, we also update the map lane with that value and a timestamp. And so yeah, you can see, yeah, the long is my timestamp, the float is the value, and then on update, we're looking at the size of the current history, and if it gets too big, we just truncate it. And we need to do that because if you're not removing that, it will just keep accumulating forever, which is not really a good thing if you're trying to do real time. But this is all very configurable too. Right now, it's doing kind of a brute force. It's like, oh, you're out of size, so I'm just going to kill the last thing because we're doing one update at a time anyway. A more robust thing, because many things could maybe be hitting this, and you can be getting more values than you're expecting. You really would want to, like, if it's greater than history size, go backwards one each, removing them. And then as you remove them, it's also going to call the UI and tell the UI to remove it. So the UI is staying in sync with this history lane. Which is also really nice because you don't have to do all that extra work in the UI to make sure it's all in sync and looking correctly. It happens because that's what SWIM does. So yeah, I think that's the kind of high level overview of the lanes. Value lanes, it's a value. It's a single value. It could be a string, it could be int, a float, it could be a JSON object, whatever you want it to be. Map lanes tend to be a list of things, and we tend to use it with timestamps, but it doesn't have to be a timestamp. It could be key indexes or whatever you want it to be. Command lanes are what we use to send commands into SWIM. And so you can actually even use a command lane from Python or from JavaScript or other places. One of our other sample applications does face detection using a HAR cascade and OpenCV in Python. but we don't have a great, well, actually, we don't have any SWIM client for Python. And so all of the results of the predictions just get sent over with a command. And so we have a lane that's basically in SWIM waiting for those commands, and we chuck them all over into SWIM, and then we can render on the UI or do other predictions or other actions based on that. So yeah, value lanes and map lanes can become really, really useful. And it's kind of like the two main things for storing your data, and then command lane comes in for kind of the external updating of things. And then join lanes are great for if you have a data set over there and a web agent over here that needs to know about it and act on it, and you don't want this business logic mixed up in this web agent. You just create a join lane, it's going to get updated automatically, and you keep all your business logic where you want it. So yeah, that is SWIM and SWIM lanes. Questions? All right, cool. Well, thank you guys.
All right, cool. Hello, everybody. My name is Ali, and thank you all for coming. I'm going to be talking about the Edge Gateway, the actual hardware product that we created using SWIM's infrastructure. But before I get into that, I would like to talk to you about who we are and what are we doing here in San Francisco. We're the innovation affiliate of Türkiye İş Bankası, which is colloquially known as İşbank, and they are the oldest bank in Turkish Republic, which is essentially the same age with the Turkish Republic, and which is like about 100 years old now. And since the invention of the computer, they have been doing their own IT stuff in their own premises until the year 2006, at which point they decided to separate their IT department as a separate entity, which would be later named as Softec. And about 2.5 years ago, Softec and İşbank collaboratively decided that they need to follow up on what's happening in the IT world, what are the latest developments, what's going on essentially, and they decided to create an outpost here in the Silicon Valley in San Francisco, which is Maxitech. And since we have founded 2.5 years ago, we've been working with İşbank and Softec to improve on their digital transformation and innovation strategies. About a year ago, we started serving other İş Group companies. There's like a big glass manufacturing company, there's a large insurance company, there are some medical institutions. And about like 6 months ago, give or take a month, we started serving external clients as well. And our primary purpose here is to find technology and try that technology and create some sort of a tangible result and relay it to our clients at the end of the day. And throughout our journey, a lot of companies that we have met, one of them is SWIM. And well, when we first heard about SWIM, we were actually very excited about what can be done with it, but we weren't really able to like identify a real-world use case that would be we would be able to take to a bank or some sort of a like financial client at the end of the day. So we, with the help of the SWIM team, we started playing around in the SWIM environment. So I'm gonna go back now. That idea actually gave us more thinking space as like what else can be done, like with the non-smart machinery turned into smart machinery at the end of the day. So since we're from Turkey, we started thinking about the Turkish environment, like where can we go? And we started thinking about production facilities. Because of the production facilities in Turkey, there's like plenty of them, but they're all very, very old. So the technology associated with them is very old, and they're not really generating any data. So this here is Turkey, in the middle of all the scary countries. And when we go to the northwest side of Turkey, other than the middle of nowhere part, there is this bioenergy power plant that we identified. And yeah, there we go. This bioenergy facility is following the model that was created in Denmark, essentially, and it's situated right in the middle of several livestock farms. And if you're familiar with bioenergy, it essentially means getting all that livestock's waste and putting it all in these big lakes and lagoons and essentially introducing bacteria into it so the bacteria can digest the waste and create methane gas, and then methane gas is burned to create energy. So this field that you're seeing here is essentially 750,000 square feet, if I'm getting my math right. I knew it in metric system, but I believe that's about like 13 to 14 football fields. So it's like a very, very large environment. And as you can see, most of it is still under construction-y kind of thing. And so we got in contact with them and asked about how they're doing what they're doing. And they essentially walked us through the thing. Like the bigger lagoons were collecting the waste, and then the gas, the bacteria was introduced. Gas is created, put into some other like digestion part. And there was aeration going on to put more oxygen into it so it burns easier. And then after the methane gas was burned, the remaining product is actually packed up and sold as fertilizer. So the owner of this facility actually tried to install some like traditional mechanisms to monitor what's going on in the facility, but he found out the prices were like very, very high. The starting price of installing the monitoring machinery was about like $150,000 US, and that was just to install it. And then it would be the maintenance, and then the entire system was dependent on wires. So there would be about like, for that size facility, it was about like 30 miles worth of cabling that is required, which just like drove the costs up and up and up. And we asked them like, okay, what is the most crucial part that you need to monitor, like for our POC stage or like trial of what we're trying to do here? And they actually identified the valves. These valves are situated around the pools that collects the waste, and well, actually the waste goes through them into the lagoon. So this valve being operable and monitorable is actually very crucial, because if you put too much in there, you're going to be destroying the diet and nothing is going to be produced. If you put too little in there, the bacteria is going to start dying because not enough food. So that's also going to be disrupting the production, and any sizable disruption is actually going to kill the facility. At the end of the day, you have to start from scratch if anything goes wrong. So we actually started playing around with the, if I can, there we go. This is a standard, very, very standard valve. This air pressure operated, and it has a PLC into like connections over there. So we decided to just like, okay, let's tap into that and create a digital twin of these valves. But the problem is, the valves, as you can see, are situated around there, and it's not really the best environment that you want to be operating in. For example, if you guys can see this guy holding a very, very large stick, well, that stick's purpose is to actually fend off the snakes that's actually coming up from there. So it's not really a nice place to go in and like put cables and like do any extended work. So we decided that it actually has to be some sort of a wireless interface to collect the information and process. So this is the summary of the problem that the owner was facing. The valves are supposed to create the homogeneity in the lagoons, and they need to be monitored and operated in real time. And the alternative monitoring systems that they actually looked into were very, very expensive, and they require cabling, but the facility is enormous, so cabling is not really feasible. And just imagine like 30 miles of cables and one of the cables broke. How are you going to find it? How are you going to take it out? How are you going to replace it? It's all creating like layers of different problems. So since there is no actually monitoring going on, the owner was employing 12 people in 3 shifts to actually go manually next to the valve, look at, yes, that's open, and now I press the button, it's closed, on paper, and then take that paper and put all the values into a spreadsheet, which would later be like reviewed. And there's an additional thing here. The production actually needs to be predicted beforehand, because not only the distributors, but the government also wants to know how much you're going to be producing that day. But if you're not really sure how much waste you're putting in there and how much bacteria is in there, you can't really identify how much you're producing. It's essentially just working on guesstimation. So the bottom line is no real-time data, no dashboard, no control over the valves. So we devised this kind of a solution here, which is essentially putting sensors on all of the valves, and those valves would be creating the real-time input, open-close data. Like, yes, this valve is closed, it has been closed since this time. and it will open, well. So there's also, since it's PLC operable, the valves already had the control circuit operation part that we can just tap into and allow them to be controlled remotely, opened or closed from a cell phone, essentially. So we put that edge gateway, our actual product, at the, well, a very close location to those valves, which would be listening to the valves over an RF frequency. We also put like a small box next to the valves themselves, which would be creating the RF frequency signals. And Edge Gateway would be then getting all the information, processing it. If there is an anomaly or there's something wrong going on, it would at least be able to show it at the end of the line at the main server. And the data being processed on the Edge Gateway actually reduces the amount of data that needs to transfer, because the valve is open, it's going to stay open for 12 hours. You don't need to keep pressing that like, yes, it's open, yes, it's open, yes, it's open. So the Edge Gateway is processing that and only sending the information when there's a change in the state. And the main server actually is just visualization and logging through, again, SWIM's infrastructure. It's essentially showing what's happening in the facility at that time in very, very real time. And the main server is actually pushing all the information that it receives to the cloud, which in turn allows the mobile application to view the data and get as close to real time as possible. At the latest trial we had like a 2-second delay, actually. So other than that, yeah, the main advantage of the edge device that we're putting there is not just it's not just there for like fun of it. It's minimizing the reaction time. Like when there's something wrong with the valves, when the valve is stuck, it's opened when it's not supposed to. Edge Gateway is capable of understanding there's something wrong going on, and then alert the necessary person who's going to be taking care of that. And also, yeah, the delays are minimized, anomaly detection has essentially no latency. And the purpose of the main server being separate from the Edge Gateway is the Edge Gateway is running essentially on a Raspberry Pi. It has very low processing power, which is fine for like checking out what's happening. But if you want to go any prediction or AI or simulation kind of way, you actually need a little bit more processing power. And that's where the main server is actually coming into play. So the main server is actually taking the information and keeping a historical log, and we are planning to, it's not there yet, but we're planning to implement an AI on there to tell us if there's something anomalous that's not supposed to happen. So the benefits of this Edge Gateway that we created, there you can see the very, very professionally created schema. But the main components is the RF antenna module that's creating the wireless communication, but it's also supporting the regular like Wi-Fi or Ethernet connection modules. The Edge Brain, which is essentially the microcomputer that we named Edge Brain, is taking care of all the processing in there, and it's basically running the SWIM EDX. The benefits essentially is like with the RF antenna, the RF is actually can actually go into a very, very large area, so there's no cabling necessary, and if there is any low signal area, you can just like put another transmitter there to just repeat the signal, so it's again strong enough to actually make it to the destination. Since it has processing power, it reduces the amount of data that needs to be transferred, and again, it's processing at the edge, so real-time anomaly detection and alert mechanisms. We're planning to implement a redundancy system to the Edge Brain, so if there's anything going wrong with that actual Edge Gateway, it will just switch to the other operating system and like keep going until the problem is fixed. We designed this gateway to be as plug-and-play as possible. Right now, it's capable of like when you attach a new sensor or a new valve or any new device in the system, it's actually capable of recognizing that and adding it to the systems that is tracking. So yeah, that's the auto sensor detection. And this actually came much, much cheaper than we expected. So this RF antenna modules are not that difficult to come by. Wi-Fi and Ethernet are also not that difficult. Raspberry Pi is very small and very cheap, so it's actually bringing the costs very, very much down. When we talked to the owner of the facility, he said that he was extremely happy about the fact that the actual monitoring system is going to be much easier to implement, and there's no need for miles and miles of cabling, and he can actually control everything from his cell phone, which is actually what's happening in Denmark, for example. Like this bioenergy facility model is used widely in Denmark, where several farms just like pool in some money and create a bioenergy facility. They feed the facility provides energy for them. So he's now actually capable of doing that, and the guy in Denmark is just like opening and closing the valves from his cell phone. So we essentially just mimicked that. And we've been working on that for the last couple of months, and we actually have some results in the point. But the PowerPoint is actually kind of being annoying here and not really showing me the video, so I have to do it the other way. Yeah, this is the first video. Here you can see how the sensors are essentially working. The valve is very simple. Like when there's the metal sheet in there, the sensors are touching it, and when it's touching the metal, it's closed. So when it's not touching it, it's open. So we mimic that. That sensors are getting it to the valve sensor part, and this is the edge gateway, which they're relating the signal to, and that is actually connecting all the way to the main server. The other video that I would like to show is here. This is them essentially demonstrating how the product works, but you can see the server actually running the SWIM interface and getting all the information, like real-time information, and then you can see the actual mobile application there. And finally, and they actually, this is yesterday, they went to the facility and got 2 of these hooked up. You can see the boxes like attached to them. The boxes are like industry standard, so they're weather and environment proof. Nothing is getting in there, so they're safe to be placed next to those horrible, horrible areas. But essentially, he's pressing the button, and with like about, I think, 4 or 5 seconds delay here, we were able to close off the valve. The next steps with this is essentially getting this infrastructure into other devices that's running the power plant. And that's not just the valves, but the actual engines that's producing, the burners, the fertilizer production areas. All of this are PLC capable, therefore can be monitored. And we're hoping the edge gateway is going to be helping this kind of small and medium-sized establishments to do that in a much, much, much cheaper way than the traditional options. But yeah, that is essentially it on my end. Do you guys have any questions? All right, well, if no other questions, thank you. And, well, that's it. Thank you.